All right, let's get started. Very good afternoon to you all, and welcome to this week's Coloquio. Just a quick announcement: we're still looking for more speakers for the remaining of the semester. This month is pretty full. Next month is also full, but May many slots are open, and June as well. So if you know a good speaker, you attended a nice talk somewhere, please forward that information to me or Sundar. And this is also a good opportunity for new postdocs or even graduate students. If you finish a new paper project, we would love to hear other people also in the department would love to hear it. So please get in touch. Okay? So today we will hear from our very own William Henney. So Will received his PhD from University of Manchester in 1992. And then he took up his first postdoc position at the Instituto de Astronomía in Mexico City. And after that, he stayed with UNAM as a researcher, a full-time researcher. And so Will wears two hats, depends on which time you catch him. Today he's not wearing any, but okay. So as a theorist, as a theorist, he's interested in radiative transfer physics, magnetohydrodynamics, and atomic physics. But as an observer, he's very much interested in looking at sources using emission-line spectroscopy. So he studies a lot of these photoionized nebulae, bow shocks, and star-forming regions. And I think by judging the title of the talk, we will hear more about those things too. Thank you so much.
Okay. Thank you, Randy. I see you use the abbreviated version of my bio, which is probably for the best, because it skips the dad jokes, which I don't always get down to well. Yeah, so do I speak in English? I'll speak in English, but that's the mindset I'm in at the moment. If anybody at any point wants me to translate anything, just say. Also, I know the policy here is that the questions are supposed to be at the end of the talk, but I'm perfectly happy if anyone wants to interrupt me for any reason, like with questions or objections. Don't worry, I won't get annoyed at. Try not to get annoyed. And that goes for the students as well, so and postdocs obviously. So anyone can stop me to ask for clarifications. So I'm going to be talking about different physical mechanisms by which massive young stars inject energy and momentum into their surroundings, particularly in the context of H2 regions. So I assume that most people here probably know what H2 regions are. A very brief introduction. This is the galactic plane seen in the light of the H-alpha recombination line from hydrogen, and it shows a lot of H2 regions which are dense, as in between about 100 and a few thousand, tens of thousand particles per centimeter cubed. Warm, typically between about 6,000 and 12,000 Kelvin, depending on the metallicity. And photoionized, that's, as I said, this is the galactic plane. This shows lots of regions. I should point on here. Lots of regions that are quite a long distance from us. Few kiloparsecs. They tend to be small and concentrated towards the galactic plane, and a few regions that are bigger and further from the plane, and these are just ones that happen to be close to us, mostly. So the same way that if we look at clouds in the sky, the ones that are far away, very close to the horizon, ones that are close to us, we see higher up and bigger. It's exactly the same with these regions. This region here, Zeta Ophiuchi, is about one of the closest, those stars to the sun, and this here Speaker is actually a B star that's even closer, but is very, very faint because it's a very low luminosity source. If we zip on, the other thing I want to see. So as well as the galactic plane, we can also see H2 regions in other galaxies. Right, you can see that here. This is the Large Magellanic Cloud and the Small Magellanic Cloud, and these are two dwarf galaxies that are companions to the Milky Way. And in smaller galaxies, the H2 regions tend to dominate more of the total emission, and that's certainly the case with these two. There are some very giant H2 regions that are very spectacular, and we're going to see a lot more about those.
Are those the Magellanic Clouds? Or?
Yes, sorry, that's the Large Magellanic Cloud is where the pointer is in the moment, and the small Magellanic Cloud is the one to the left and a bit down.
So does it mean that the galactic center is more or less in the center of the photograph? Or?
Yeah, that could be the right.
Yeah, it's the most extreme.
Yes, yes, I think so. Because Orion is sort of close to the anti-center.
Okay.
So if that's the whole galactic plane, yeah. I'm not 100% convinced, but I think you're probably right. Okay, so this is like a slight zoom in on the region around Orion and the nearby galactic plane, like IRyA, more or less, where it joins the plane. And we can see that, again, there is a vast variety of scales. Not all the variation, and I said that a lot of variation in size is due to apparent parallax from the just different distances, but there's also a large variation in the intrinsic size. For instance, in Orion, in the constellation of Orion, all these regions are more or less the same distance from us, 400 to 500 parsecs. Yet they're very different sizes. This is that's called Barnard's loop. That's tens of hundreds of parsecs across. Lambda Orionis also tens of parsecs. Sigma Orionis tens of parsecs. The Orion nebula itself is very bright. It's hardly resolved here. It's only a few parsecs in size, and then they're all inside an even bigger structure, which you can't really see the full extent of here, which is called the Orion-Eridanus superbubble, which is on the scale of kiloparsecs and seems to be breaking out of the galactic disk. Okay, so previously I've just been showing the emission from the gas, but really to have a better view of things, we need to see what the relation is between the different components. And here we're showing the star's gas and the dust all together. So the H alpha again is in red on this, whereas the white emission is continuum, which is mainly from the billions of stars in the Milky Way. And the brown bits are due to the reddening and extinction of the background stars and background gas emission from the dust. And we see that the H2 regions are often associated with dark clouds. And that's because they form from the action of the high mass stars, and the high mass stars do not live very long, so they never get very far from their points of origin in the molecular clouds. Apart from James' talk the other week, which was about precisely how they could get along with. But those were exceptions. Most of them stay quite close to their point of origin. Okay, so that's enough pretty pictures for the moment. We'll get back to pretty pictures later. But first of all, we're going to have to consider a little bit of physics. So in the lower luminosity regions that are ionized by single stars, like an 9 star or an 07 star that has masses between about 20 and 40 times the mass of the Sun, then it turns out that dynamics is mainly dominated by thermal pressure gradients. So that's what this is that if you heat the gas, then you increase its pressure with respect to its surroundings, and that difference in pressure causes an acceleration, a force causes an acceleration, causes the region to expand. And that's the general idea of this old classical work done by Spitzer on this that has a spherical expansion in a uniform medium. And the reason that the thermal pressure dominates is that inside the H2 region, the ionized sound speed is about 10 kilometers a second. That's the speed with which thermal pressure pulses can be transmitted within the region. And this is generally larger than the alphane speed, which is the speed at which magnetic disturbances can be transmitted. And it's also larger than the escape velocity. That's for typical reasons. Obviously, there are going to be exceptions. There are some regions that seem to be highly magnetized. And if you manage to get a very large amount of molecular gas on scales of tens, hundreds of parsecs, then the gravity will start to become important. But that's not typically the case in galactic molecular clouds and H2 regions, and so we're dominated by the thermal pressure. And this causes expansion, which initially is about the sound speed of 10 kilometers a second, but eventually slows down. And if you try and do simulations of how this evolution proceeds in a uniform medium, even adding magnetic fields, we have a magnetic field parallel to this direction, which helps to break the expansion in this direction, but doesn't stop it in this direction. That's why this is elongated. But still, the whole evolution is a bit boring. The pressure drops as the H2 region expands, and once the expansion has increased in size by a factor of roughly 10, then it gets into pressure equilibrium of its medium, at which point it sort of just stops. It doesn't do anything. Luckily, that's not what happens. Or at least, it's not what happens in simulations that are slightly more complex than that, and also it doesn't seem to happen in real life. It doesn't happen because the density in which the H2 region is expanding is not likely to be uniform. And if it has condensations of higher density, then these slow down the propagation of the ionization front. The ionization front wraps around it, it squeezes down and compresses to form a sort of high density globule by driving shocks into it. And at the same time, the ionization front changes its nature. In the normal expansion, it's a concave ionization front. The gas can't go anywhere once it becomes ionized, and as a result, it just stays there hanging around and reduces the amount of flux reaching the ionization front, and therefore giving a rather boring dynamics. Whereas in the case where the ionization front wraps around, the geometry is convex, the flow from the ionization front can diverge, but accelerate and reach sound speeds of order 2 or 3, and can drive transonic turbulence inside the H2 region. And that's what we're seeing in these rather old simulations that I did with collaboration with Enrique. Enrique gave me the initial conditions, and then we did the physics of the H2 region. Okay. So a bit more detail on talking about these globule flows. So these are from some other simulations in which we were doing like zoom-in simulations of particular globules, and including the effects of the magnetic fields. So here you show that the shock's driven into the neutral globule, and then we have the flow of rather fast, like 10 to 20 kilometers a second flow of gas off the globule surface. Obviously, that's not fast compared with some things, but for the amounts of H2 regions, it's reasonably speedy. Okay, so of course, you're always going to have a tension between the local and the global geometry, because even though we have a local convex ionization front and we have a divergent flow, eventually this flow is going to have to reckon with the fact that it's inside an enclosed region, and so globally the whole thing is going to be concave, and it's then going to end up shocking against the material that's already there. And we'll see some examples of that in a moment. Okay. I'm going to jump out. These are just this in case I wanted to talk in more detail about these videos, but we might come back to that later if I have time. Okay, so in summary, this is something that I worked out an analytic theory of actually before we did the simulations. That you get to a sort of steady state with the globule flows, because the dynamical times for the globule flows are shorter than the expansion timescale of the region, because the velocities are similar and the sizes are smaller. And so you can have a sort of like self-synchronous expansion of these essentially fixed structures, in which the globule flow accelerates until if the same time as pressure is decreasing, ground pressure is decreasing until it comes into pressure equilibrium with the rest of the H2 region, which in this case we're simply pretending is a constant density. In reality, we'll have fluctuations, but this is just to give a first idea. And what this means is that you'll be able to carve out these cavities around the globules, but the size of the cavity is going to be proportional to the size of your ionization center on your globule. Small globules are going to make small cavities, large globules are going to take larger cavities on average. And then also the density at the base of these photoevaporation flows can be boosted by factors of up to about 10 with respect to the average density in the H2 region. That's when the globules are close to the global ionization flow. If the globules are supposed to survive in the interior, then they can have densities on their ionization functions that are far higher. We see that, for instance, with the protons in Orion, where they have densities of up to about 10 to the 6, as opposed to densities of about 1,000 being typical ones in the H2 region. These are from the same simulations we showed in the video. So, you might think, well, okay, well, that's just your work. What about other people? Maybe they can find the same thing. They do find it. They never talk about it, but they do find it, and sometimes you see it in the figures. This is a simulation which, on paper, well, I'm sure in reality, is far more sophisticated than the one that we did. They were doing, Enrique's group has also done similar simulations in which they did the formation of the molecular clouds, the formations of a cluster of massive stars, and the effect of the ionizing radiation from these newly formed massive stars on the heterogeneous surrounding density structures. And here also they found that you find these globule structures, they make cavities and they shock against the general ionized gas. A lot of these things that you see that look like cavities that don't have anything associated with them, that's because these are slices through the cube. And so in these cases, the actual globule is not in the plane, it's in a different plane. But you see the effect of its cavity, you don't see the globule. Okay, so I've been talking a lot about thermal pressure gradients, and how that works well for lower luminosity regions. But we know that on a larger scale, it can't be enough, because when we look at the velocity dispersion in H2 regions, either from the line of sight velocities from the line widths, or from the plane of sky velocities from looking at the variations in the line centroids, you find that the lower luminosity regions have velocity dispersions that are subsonic or transonic. Whereas once you go above about 100 times the luminosity of Orion, you find that the velocity dispersions start to become significantly supersonic. And it'd be very hard to do that with thermal pressure gradients, because you get diminishing returns. You can accelerate. If you can keep the gas isothermal, you can theoretically accelerate it to infinite velocity, but that only happens logarithmically, and it only works so long as the heating and cooling timescales are shorter than the dynamic timescales. And as the density drops, heating and cooling timescales get longer, and you get to the point where you cannot maintain the isothermal condition. It transitions to an adiabatic flow, in which case the velocity tends to a constant value. And that typically happens at about 3 or 4 times the sound speed. You might think, well, 3 or 4 times the sound speed to get you up to here. But yeah, that's the really low density gas. So if you actually calculate the dispersion, which ends up being usually weighted by the density squared, if it's from the line widths, then the dispersion is far higher than that, is far lower, sorry, than the maximum velocities. And so I keep forgetting to use the pointer, don't I? Apologise to the Zoom people. So what I was saying was that the velocities we can reach from thermal pressure gradients are up here, but that's in a very small fraction of the total gas. If we calculate the velocity dispersion of the whole region, it would end up being the sound speed or lower. And so these line widths that we see can't be explained by thermal pressure gradients, we need something else. Okay. So the obvious thing, the one people have thought about this a lot, is that we could be something to do with radiation, or what is almost equivalent the wings. Okay, the reason that there is an equivalence between the radiation and the wings is that in massive stars, the wings are radiatively driven. And so there's a proportionality between the momentum loss in radiation and the momentum loss in the wings. We'll talk a bit more about that in a moment. So we can lump them together, and in order to simplify things enormously, we can just make a global comparison of what the maximum radiative force of the starlight could be in its surroundings, and compare that with the thermal force to do with the thermal pressure of the H2 region pushing on the neutral gas outside. Okay, so the radiative force is just the rate of loss of momentum in the radiation field, which is simply this luminosity of the star divided by the sound speed, light speed. But the thermal force is the thermal pressure, which is twice NKT, twice because if it's mostly hydrogen, then we have 2 particles per hydrogen because we have the proton and the electron. That thermal pressure multiplied by the area of the ionization flux, which again, I'm not showing you. So the other thing we can use in order to simplify things is we can assume that we are in photoionization equilibrium. That is that globally the number of ionizing photons per second emitted from the star is equal to the recombination rate in the ionized gas. Now, there are various things that might affect this, like you can have photons that escape from the region, so they shouldn't be counted. You can have photons that are absorbed by dust in the H2 region. So there could be a correction factor. Also, you can have like advection of new neutrals into the H2 region. That turns out to be very small in most cases. So at least this is a reasonable order of magnitude estimate. So by combining these, we can actually find that the ratio of these 2 forces, that is the radiative force against the thermal pressure force, can be expressed very simply in terms of 2 things. The first is the ratio between the mean photon energy and the mean particle energy, which is the term in parentheses here. The mean photon energy is the mean photon energy per ionizing photon. So it's equal to the bolometric luminosity divided by the ionizing photon rate. You can actually show that this actually has to be strictly larger than the ionization potential of hydrogen. It's typically about 20 to 30 electron volts. The thermal energy per particle is like 2 electron volts if temperature's 10 to the 4. And then that multiplies by another factor, which is the global ionization parameter. Now, the ionization parameter is a dimensionless number that's equal to the ratio of the density of ionizing photons per centimeter cubed in the nebula divided by the density of hydrogen in the nebula. And again, it's a global thing, so it's not like an average value of that. And it turns out that this ratio between the radiative force and the thermal force should be equal to 10 times the ionization current, which is really nice result. So what is this ionization current? Well, again, it's nice that it varies very little in H2 regions. It's something that you can determine really by looking at the ratios of emission lines with different ionization stages. So it's very well constrained observationally. And you find that it does vary, but it varies in a very small range, between about 10 to the minus 3 and 10 to the minus 2. And it does vary with the luminosity and the density. You can show that for classical Sturmgeon sphere, it should have this functional dependence. So it's proportional to the product of the ionizing photon rate of the stars multiplied by the density, but then very slowly, only varying as the third power of that. Also, that's assuming that the whole volume is filled with ionized gas. So you assume the ionized gas is confined to a thin layer, as it might be if you were to push it with radiation of the winds, then that can only reduce the ionization parameter. It's proportional to the value for a filled sphere multiplied by 3 times the thickness divided by the radius in the limit of small thickness. And so if you look at that, you compare this ionization parameter, which is less than 1%, and that this ratio of forces is just 10 times the ionization parameter, then you come to the conclusion that, well, the winds and radiation are never actually going to be dominant. So, is that correct or not? Well, maybe it is, but we are missing some important factors. So, the winds, so in order to really to include winds in this scheme of just using the radiative force, we need to take into account the efficiency of the driving of the wind. This is a factor that's usually less than 1. It has to be less than 1 if the wind's optically thin, because then you only have single scattering. And it's typical, and this is the ratio between the momentum loss in the wind, mass loss rate times velocity, and the momentum loss in the radiation. And for low luminosity stars like B stars, it's very low. It can be like less than 1%. For the more luminous O stars, which are of the brighter H2 region, it does get to be more than 0.1 to 0.5. And in evolved high mass stars, in particular Wolf-Rayet stars, which have optically thick winds, and you can have multiple scattering, therefore the momentum of each photon gets used several times before it gets out to the base of the wind, they can have this momentum efficiency factor greater than 1. And also it tends to scale with metallicity because the driving of the winds is from the metal ions, carbon 4, nitrogen 5, whatever in the winds, and with lower abundances, this driving is less efficient. So you would expect that this to be reduced in low metallicity environments. Okay, so that's an efficiency factor that's less than 1, or of order 1. But you also have what I'm calling boost factors. I'm not sure anyone else calls it that. I think it was called. But this boost factor is the increase in the effectiveness of the wind in pushing on the material in the H2 region. And this is bigger than 1, mainly because in the simulations show that when you're in the turbulent H2 region, then you don't have a nice spherical shell. You have a very sort of undulating shell, and this increases the effective area of interaction between the hot wind and the H2 region, and means you're more effective at pushing it. And this it doesn't really get as high as 10, but it can be almost as high as 10. But even including these, you get to the idea that the ratio between the force due to the winds and the force due to the thermal pressure has to be less than 1. There are exceptions. If you allow what's called energy-driven winds, then all bets are off, because this means that you can bottle up the pressure in the hot wind bubble, and so that you don't just have a direct accounting of the momentum balance, because the only thing that's stopping you driving things forever is energy conservation, not momentum conservation. But energy-driven winds are generally believed to not occur in reality. You don't quite have momentum-driven ones either. In fact, so part of the fact this is bigger than 1 is because there is the fact that the shock wind is a thick region means that you have a slight increase in the efficiency of the driving of the shaded draft. But the conclusion is that you can't actually push all of the H2 region down into a tiny thin shell and directly push on the neutral gas with the wind. At least in most galactic H2 regions and ones in nearby galaxies. If the luminosity is high enough, then you probably can, but that would be like different sorts of regions. Okay, so here are some recent simulations by Lancaster et al. Precisely this effect. These did lots of analytic calculations as well. Now, this is my interpretation of his results. He doesn't say explicitly this in his papers, but I think it's quite apparent from his figures. So what we get is a free-flowing wind that shocks, makes a hot bubble, which is trying to drive into the H2 region. At the same time, the photons, ionizing photons have ionized the H2 region, form these globules that we talked about earlier. These are having these photoevaporation flows that are making the cavities, but instead of shocking against the just general gas of the H2 region, now these photoevaporation flows shock against the hot wind, the hot bubble of the stellar wind, and this forms a rather thick shocked shell. So all the stuff that's in white here is material that's from the H2 region, from the molecular cloud that's been photoionized, and is then being sort of accelerating the photoevaporation flow, and then is shocked against the obstacle that's in the middle and form this shocked shell. Whereas the things labeled in black are things that came from the start. Like there's the supersonic wind, and then there's the hot shock wind that makes the hot bubble. But what this means is that because there is a supersonic or mildly supersonic phase of this photoevaporation flow in between the globule and the shocked shell, this means from a hydrodynamical point of view, they are causally disconnected. And so there's nothing the wind can do hydrodynamically to affect the neutral molecular globules, because this photoevaporation flow is effectively shielding it and making this sort of causal barrier that prevents any sound waves from the hot bubble from reaching the ionized gas. The neutral gas. Okay, so we think that maybe I should have just talked a little bit more about this. So the upshot of this is that the wind can have a large perturbation effect on the H2 region, on the ionized gas. It can change the kinematics of the ionized gas, change its distribution, its spatial distribution, but it's not going to affect the neutral and the molecular gas. So observationally, you would expect to see, if this were the case, to see elevated dispersion in the ionized gas without any accompanying elevated dispersion in the neutral and molecular gas.
Are those simulations also the initial condition is turbulence?
I think so, but I think it was just done by some sort of fractional Brownian motion, then of just assuming a power spectrum and constructing an artificial density field. It didn't actually come from simulations of the actual molecular cloud formation process.
O-star? O-B-star?
Oh, it's a cluster. Right, so this is an extra detail that I neglected to mention. When you've got many stars, then you can't add their stellar winds. Right? You can add their photons, because the photons don't interact, so they can just pass through one another. You can't add their winds. If you've got lots of stars, then the cluster, all the winds just shock against each other. And what you form is that you form a sort of a big ball of hot gas. And this ball of hot gas, which extends to the whole, for the whole region in which you have the stars with the powerful winds, at the edge of it the gas accelerates transonically in a very similar way to these photoevaporation flows. But the difference is that instead of having 10 to the 4 Kelvin gas, you've got millions of Kelvin gas. But you have a transonic photoevaporation flow, well, not photoevaporation, right? The transonic sort of wind of this thermal wind from this hot cluster core, and this forms what's called the cluster wind. And it's that cluster wind that accelerates to Mach numbers of 3 or 4 and then shocks again. Okay, so this is all shocked lots of times in there, and then it comes out and shocks again. Of course, they don't simulate what goes on in there, they just assume. There are people who simulate what goes on in there, and it turns out to be a bit more interesting than I just explained, but we haven't got time to get into it. Okay. Right, so if the wind can accelerate the ionized gas but not the neutral gas, what about the actual direct effect of the radiation? So this also has its efficiency factor, and the most important one is the optical depth, because the optical depth determines the fraction of the radiation that's absorbed. So if the optical depth is very small, then you can have an enormous radiation pressure, but it doesn't have any effect, because it just all goes right through everything, and the very small fraction is absorbed. Okay, so there are various types of radiation pressure that we need to consider. The three main ones are the ionizing radiation, that directly acts on the trace fraction of neutral gas in the H2 region. That does have a large optical depth, but on the other hand, it doesn't do very much. Then things that are in theory, on a global scale, could be more important is the FUV continuum that primarily is absorbed by dust, and the Lyman alpha resonant line structure. Okay, so the FUV continuum on dust could be important, but not in the H2 region, because even if you assume that the dust all survives inside the H2 region, it turns out that the total column of dust in the H2 region means that the optical depth is 10.1 or less usually, and so a small fraction of the FUV radiation is absorbed inside the ionized gas, and it's probably worse than that because lots of evidence that at least partially the abundance of dust is reduced inside the H2 regions by factors of like 3 to 10. So all that tends to suppress the effects of the continuum radiation pressure. But on the other hand, once you get into the neutral gas, then that's where all that FUV continuum is absorbed in the photodissociation region, where it excites the PAH emission, for instance, which is very bright in there. So we just know from looking at the PAHs more or less where all this FUV continuum is absorbed, and there it could have a role in determining the dynamics, but it still doesn't seem to be that right. On the other hand, Lyman alpha is, well, on the one hand, it's a lot more complicated to deal with, because Lyman alpha, instead of being just continuum that has a rather simple absorption and emission processing, this is a line. It's a resonant line, which means that I was talking to my interstellar medium students about this today, so see if I remember it. The resonant lines are transitions between the ground state and the next excited state in an atom or ion. And they are special because when you radiatively excite the upper level, there's nowhere it can go other than back to the ground state. Which means that when you absorb the line, you might re-emit it, later be absorbed again, and then re-emitted, and then absorbed, and then re-emitted. And it turns out that the optical depth in the H2 region, even though the H2 region is 99.99% ionized, the optical depth of the neutral hydrogen to Lyman alpha in the H2 region is extremely high, 10 to the 4th. Okay, so the question is, why am I saying that the effective tau is low? Well, that's because the Lyman alpha line diffuses in frequency mainly because of the expansion of the H2 region. If the H2 region is generally expanded, then each part of it is moving away from most of the other parts. And so every time that an emission line is scattered, it gets shifted slightly further to the right. And this quite effectively moves the Lyman alpha from the line center where the opacity, where the optical depth is enormous. It moves it into the line wings, particularly the red line wing, and slightly into the blue as well, where the optical depth is small. And then once it gets into the line wings where the optical depth is less than 1, it can get out of the H2 region. But most directions out of the H2 region, all there is more hydrogen, and this hydrogen is neutral. So this has a far higher column density than the neutral hydrogen in the H2 region, and instead of having an optical depth of 10 to the 4 like it has in the H2 region, in the neutral PDR, it has an optical depth of 10 to the 6 or 10 to the 8. And so it gets pushed even more. And so it bangs around inside the neutral gas, and occasionally one comes out and comes back into the H2 region. But the ones that come out into the H2 region, because they've been in a medium that has such a high optical depth, they've been moved so far into the wings of the Lyman alpha line that the H2 region is completely transparent to them. So the upshot is that Lyman alpha can be very important, but it will not affect the ionized gas, or hardly at all. But it can affect the neutral gas, because it can push directly on the neutral gas. So if Lyman alpha was important, then you would expect something different. We would expect high velocity dispersions in both the neutral gas and in the ionized. And it also has this extra thing that, according to some very nice, very elegant recent work on this, both numerical and analytical, in certain circumstances, you can actually get this boost factor for the momentum of which Lyman alpha can push things, and it's like factors of 10 to 100. Now, to be sure, this works best when you've got no dust. Okay, so it works best at low metallicities, because if you have dust, then the dust competes with the neutral hydrogen for absorbing these, for interacting with these lines, and it effectively destroy the Lyman alpha. Although I had this like really simple analytic equation for how that works that I published like 20 to 30 years ago. Lots of people cited it, and then when these people came along and looked at it in more detail, it turns out that it was total rubbish. Well, it's not total rubbish, but it just has some assumptions baked into it that turn out not to be always valid. So it is possible that even in the case of dust, you might be able to get quite high boost factors. But it also relies on a sort of bottling up effect, similar to the energy-driven winds. It requires like the Lyman alpha photons to be rattling around inside the cloud, going from one side to the other. And if there's any sort of small hole where there's a low optical depth line of sight to the interstellar medium, to the low density stuff, then these Lyman alpha photons can escape through that, and that tends to sort of deflate the balloon. So it's not entirely clear how much Lyman alpha is going to do, but in principle it might be interesting. Okay, I'm going to go really fast. Right, so that's all fine in theory, but what do we see when we look at actual H2 regions? Okay, so the low luminosity regions do seem to have clear evidence that winds are present, but are confined to very small regions. Okay, so this is C2 Beauty, that's H2 region that's very close to us. It's around 9 star, I think. And you can see the size of the ionized region, and we have a little bow shock in the middle that's powered by the wind of the star interacting with the flow of ionized gas. This is actually an interesting region because the star is a runaway. It's moving at about 30 kilometers a second through the interstellar medium. So you have an R-type ionization from in this. And so the whole gas has a sort of systematic velocity through this region, and that's what interacts with the stellar wind from the star, but it happens very close to the star. It shows that the stellar wind momentum must be very small compared to the momentum of the gas in the H2 region. Well, I forgot to translate that. Well, okay, so there's different sorts of interaction arcs we can have, depending on whether it's the radiation or the wind that's supporting the arc, and also whether the dust is well coupled to the gas or is weakly coupled to the gas compared to the radiation forces. But the most common one is just a normal boring hydrodynamic bow shock. When we start to go up in luminosity to like Orion type regions, then it's not entirely clear what's going on with the stellar wind. We have there's two parts of the Orion nebula where we have very strong indications that the wind is doing something. One of which you can't really see here, is very close to the center. We have the croplets, which are evaporating protostellar disks, and the photoevaporation flows from these can be seen to interact with the wind from the high mass stars, forming interaction arcs similar to what we saw in Sigma Orionis. Sorry, not Sigma Orionis, in Zeta Fucus. Okay, so that occurs in this tiny little bit in here. And then on much larger scales of like 2 to 4 parsecs, we see X-rays from an extended region, but only on one side of the nebula. And it's like a long way away from where all the ionizing stars are. This is probably a lot to do with foreground extinction, because this is a region with foreground extinction of AV about 0.1, whereas the whole interior region here has AV of order 1 to 2. So it could be that the column density of the foreground gas is stopping us from seeing any X-rays from in the centre. But it's a bit frustrating that we can't see more evidence of the effect of stellar winds in Orion. If we look for evidence in the kinematics of the photoionized gas as well, nothing is very clear. So we're going to skip that and go to somewhere with this clear gas, which is more luminous regions. So these are giant H2 regions that have much more massive stars in them. In Orion, we have really one dominant massive star and a couple of O9 stars. But in more massive regions, we have multiple O4, O3, O2 type stars. We have ultraviolet stars if they're more than a few million years old. And here they expect the winds to be much more powerful. And that's precisely what we see. We're going to concentrate on Kishmish 24, because that one has some beautiful imagery from the JWST. Okay, so I made a mistake here. These pictures are not JWST. The one's JWST is this one. I just forgot to change the labels on the other, so I apologise. So what's going on here? So we have this is a massive cluster, and one of the most massive member of it is not just a single star, but it's a triple star. Just try and be a word. I'm not sure. I don't think it put a squiggly red line in there. So this has a very powerful wind, and it seems to be forming this interaction shell here. Okay, so and this is all part of a much larger superbubble, in which the dynamics is probably dominated by supernova remnants. Well, this part here in the middle should be just the H2 region in the stellar wind. So looking a bit more closely at that, this is my interpretation of what's going on. But just like in those simulations, we have the stellar wind. I'm drawing these lines going all the way here. In reality, these lines should stop somewhere around here, and we should have a large, thick, hot wind bubble here. But the hot wind bubble we don't see, because it emits X-rays, but I don't think I don't think any of the X-ray telescopes have enough resolution to see what's going on in X-rays here. There are X-rays of the observations of this region. Maybe Jesus should look at them. So at the same time, we have a photoevaporation flow that's coming from these globules, just like in the simulations, and this photoevaporation flow gets the transonic velocities and then shocks against the obstacle of the stellar window, forming this shape. That's the idea. And we see that here, this is like a perfect encapsulation of what we were saying about the most massive clusters in the simulations. They should form these stellar winds, shock stellar wind shells, but these are causally separated from the molecular nucleus. Okay. This is just to say there's similar physical processes occurring circumferential nebulae as well. These are all of the globules in a ultrafilament nebula around a ring nebula, around ring nebula, and a voltaic star. Now we also see photoevaporated globules and interaction through the stellar wind. This is from Roberto's thesis. Okay, so now on to the final part. In the last 5 minutes of my talk, I'm going to talk about 30 Doradus, which is another giant H2 region, even more luminous than the Vishnu 24. And this is in the Magellanic Cloud, so it's a distance of 50 kiloparsec. This is another beautiful JWST image at mid-infrared wavelengths, where the red-orange emission we see is a combination of PAH emission from the photodissociation region and also molecular hydrogen, I think, which also comes in the photodissociation region. So that's all in the neutral molecular part. And then the white is the emission from hydrogen, principally from hydrogen recombination lines that emit in the mid-infrared that come from the ionized gas. And then the blue is stars. So this you see has a complicated structure, filamentary structure. It does seem to have some sort of bubble in the middle of it, and the region around the stars, at least in projection, does seem to be relatively devoid of gas, although of course there are some things that are projected there. And there's some strange holes in it, like over here. So this is a new project, new for me project, that we're going to be using the local volume mapper of the Sloan Digital Sky Survey. This is some small telescopes, 4 16-centimeter telescopes, that are connected to really sort of top-of-the-line medium resolution spectrographs that are fed by fibers. So they have these integral field units. We get a three-dimensional view. We get position on the plane of the sky. And we also get a spectrum over the whole range of from the blue to the near infrared. And it's surveying the entire galactic plane and the Magellanic Clouds. And a lot of people, including a lot of people at the UNAM, in the Institute of Astronomía in Mexico City and Ensenada, have been working very hard on this in the last few years. And this is my small contribution to it. So we can map the emission lines from in this case the H alpha line coming from the whole area of the 30 Doradus nebula. This is a much larger field than was shown on that JWST image. This is the brightness, and at the same time, because we have the spectra, we can measure the velocities. So this is making a map of what the mean velocity is as a function of position on the sky. And we see that it varies by over a range of about 80 kilometers a second. So if you actually calculate the dispersion of this, it comes out to about 15 to 20 kilometers a second. So here we're on the boundary of regions that we think must need winds or radiation in order to explain. These are the line widths. This project with IRyA is an extension of something we've done previously using MUSE. But with MUSE, we have a very small field of view of, this is each exposure is 1 light minute squared. There's 4 of them here. This is 2 light minutes, but we have very high resolution. Whereas with LVM, we have a much wider field of view. Well, of course, we have much poorer resolution in the central region. But even so, comparing the two in the region of overlap, it's actually remarkable how good the LVM results are, given that the actual size of the fibers is this, like it's 35 arc seconds diameter, but we managed to get a resolution even better than that from multiple exposures with slight movements between them. It gives like sub-pixel dithering pattern, which gives you pretty good agreement with the MUSE observations. And of course, this is just 2 arc minutes, whereas the actual full field is nearly a degree here. Well, in fact, it covers the entire galaxy, but the reason we're looking at is nearly a degree. So, very preliminary results. We're looking at the relationship between the intensity, the 0th moment, the 2nd moment, the 1st moment, the dispersion, and the mean velocity. And well, I don't have time to talk about it, but it's going to be very interesting comparing what's going on at the small scales in the center of the cluster and what's occurring at the larger scales, and also, and more importantly, comparing the H alpha with CO and H1 in order to compare the dynamics of the ionized gas with the neutral gas and the molecular gas. And some preliminary results of that, which actually from 2 days ago, seem to show, at least by looking at it, that you have more variation in the ionized gas than you do in the molecular gas, which is evidence for what I was talking about, the effects of winds affecting the H2 region without affecting the neutral molecular globules. And finally, there's from the JWST imaging, there's also some direct evidence for interactions between globules and the stellar winds. If you zoom in on this area here, you see this little globule that seems to have like a power shock arc here. So I'll just leave you with the summary and say thank you, and if you want to ask any questions.
Thank you, Will. We have some time for questions.
Did you try looking for the iron coronal lines in the optical? Remember I mentioned that?
Yeah. Which line was that?
It's iron 16 and 14. So yeah, about 4,000, 5,000 amps.
It's just the emission measure is going to be so low. That's the
The X-ray is produced because of the X-ray emission. So, and it's a lot of X-ray emission. 30.
No, I realised when I was like going through this talk, just when I'm getting it, probably 90% of the things on X-rays I meant to add to the talk, I didn't add to it. So you could give a sort of follow-up on the X-ray side of this sort of work.
Occasionally, I have needed to look in the literature for this question that you addressed. What was the dominant force in these 2 regions? And when I look for it, I find like contradictory papers. I never know what to make of it. For example, what do you think of this series of papers by Laura Lopez and so simulations like Coloquio, that they show that the radiation on a large fraction of the parameter space radiation pressure is the most important dynamical.
Well, it can, but it could be on the not on the ionized gas.
No, on the what?
It couldn't be on the ionized gas. And I don't think that for the sort of normal galactic regions, I don't think it would be on the neutral gas.
Well, you know that there are other papers that say that.
There are a lot of papers that say a lot of things. a lot of them are way too complicated. They make things too complicated.
Because occasionally they have listed this for interpretations of the embedded H radios that I see. So then I look in the literature and I keep finding like essentially contradictory statements.
So she argues that the hot gas X-ray emitting pressure is smaller than the ionized region. But she did it with the Rosat observations. What Rosat observations you don't resolve stars and so
yeah, as I say, the things with the come-up, it's all very hand-waving and empirical, and you've got lots of things that are superimposed on each other, and they make a lot of assumptions, and try and derive a pressure. But I don't know how reliable it is. Yeah. So but there's lots of groups who seem to converge on more or less the same conclusions. Like what I'm saying is consistent with at least all of the Ostriker group work. So pretty high level of confidence that it's correct.
Yeah, so if I can summarize your results, could I say then that, summarize the summary. Then the expansion of the H2 region is dominated by thermal pressure. Is that a valid statement?
Well, unless Lyman alpha is important. Lyman alpha is really the other process that has the best chance of dominating the expansion because it can act directly on the neutral material. Yeah, so if you push away all the neutral gas, then of course the ionized gas is going to go with it.
Yeah, because for our purposes, we're interested in particular on what is the main destructing agent on the parent molecular cloud coming from the massive stars. So and we sort of like the idea that it's mainly the thermal pressure because that's the only thing that we put in our simulation. So we want to know whether we are very far off or not very far off. And then a secondary question would be, does the fact that the radiation pressure seems to affect the ionized gas and make it so perhaps it makes it more turbulent, did I understand? Or
the wind interacts with the ionized gas.
Does it have like a secondary effect on how the combined effect of all of the radiation, the thermal pressure and the wind drive the destruction of the surrounding molecular gas?
I have no idea. I don't because what would be the destruction mechanism?
For us,
just evaporation of it. You just photo evaporation.
Yeah.
Yeah. Well, if the wind is sufficiently strong to push the ionized, push the interaction shell on down close to the globule ionization front, then that can affect the photoevaporation rate. Whether it would increase it or decrease it, I'm not entirely sure. Anything that pushes the globules further away is going to decrease the photoionization rate. But of course, once they've gone out of the way, then maybe you consider them destroyed anyway, because they're just not in an interesting place. The other point that just occurred to me is that because I'm obsessed with the globules and the photoevaporation flows, I sometimes forget that they only represent a fraction of the total directions from the star. So there always has to be at least some parts, some lines of sight from the ionizing stars, which is more like a classical Sturmgren sphere or a Spitzer type expansion. And so I haven't actually run the numbers there as to whether the winds would have an effect or not. It may be that in those lower density directions from the star that the winds could have more of an effect. Yes.
So if you have a star, a globe, and that is generating a shadow behind it, but you're going to have, you're just saying, in this direction you have the typical Sturmgren expansion, but then you have the shadow, and some of the energy is going to go into pushing this ionizing and pushing the shadow away. So you're saying that that is not going to be a strong effect because the globules are a small solid angle?
No, that wasn't what I was saying. What I was saying was that the region where there is no globule is not the shadow, it's the bit that's like a normal H2, a normal sort of concave H2 region that's expanding in lower density gas.
Yes.
Those are the bits that I don't give enough consideration to, and I should. The shadow thing's interesting because depending on the parameters, the shadows can either accrete material or they can be photoevaporated themselves by the diffuse radiation. Coloquio and Alex Radin did a lot of analytical and semi-analytical studies of that.
Well, I got a little confused about this the image that you showed of the globules and the cavities. Can you put it again?
Which one?
One of the first at the beginning.
Okay, the beginning of the
From the simulations.
Let's go fast. Time to stop.
Maybe, yeah, over there, a little bit later. Yeah, that one.
Yeah.
So you have, you mentioned that you have the globule and you have a cavity.
Yes.
But in my mind, you have like this N0 region of the H2 region as a lower density than the short region, isn't it? So
Okay.
why is a cavity? I'm a little confused on that.
The cavity is because the ionization front is over pressured with respect to the general density in the H2 region, which means that it can expand. When it expands, it becomes transonic, the density falls, the ram pressure falls until it gets to where the ram pressure of this transonic flow is equal to the thermal pressure in the H2 region. And there it shocks. But there's only one shock. It's not like in the wind interaction, there are two shocks in each wind. Here, you have one wind and one subsonic region. So you only get one shock, so you just have a cavity, you don't have a shell, you just have a border to the cavity.
Okay.
If there's a wind, then you get a shell instead.
So is there after me today?
Yeah.
Are there any Zoom questions?
Yeah, I don't think there's any. Check this one. Is there a question on Zoom? I see something now.
Well, here you are.
No, there are. Yes, so Rogelio has a question, which he typed in. The question is, he says, how much does a supernova influence the expansion of the H2 region? Do you think this is a necessary ingredient to take into account to explain H2 region dynamics?
Oh, okay. This is the elephant in the room. Supernovae on a global scale in the galaxy energetically dominate everything else. So once the supernovas start going off, yeah, this is happening. But we have a little corner of the universe that we can study before the supernova goes in. But yes, that is a good point, and I should have emphasized that. This is pre-supernova feedback.
Wait, let's thank Will again. He was not.